Hi, my name is Loris Fanzo. I teach and research at Southampton University, and this little treatise is another member of the family of space-time shift keying oriented publications in our current research portfolio. We at Southampton Wireless are quite interested in the spatial modulation family, and so if you visit our website you would find a whole number of related treatises. And so just to really talk about the evolution of spatial modulation a little bit. So of course in the MIMO era there is a further benefit in using this principle in the antenna domain, because if we activate only, for example, 1 out of 4 antennas as seen in this picture, then we only need a single radio frequency chain. Of course, there's a price to pay, because in this particular case, we don't get a transmit diversity gain. And so this family of modulation schemes inspired quite a lot of recent research. We also published a large survey and tutorial treatise on the subject. But let me delve in a little more detail to talk about these derivatives of the spatial modulation family. So with my valued friend and colleague Shinya Sugiura, we designed space-time shift keying, where the philosophy is that instead of using a single transmit antenna, we actually use a number of spreading matrices to select on the basis of the information to be transmitted. So we lose this way the benefit of having a single radio frequency chain. However, we are able to gain transmit diversity again. So over the past couple of years, we've been looking at various compromise schemes as well, and we found that with the aid of antenna selection, we can actually strike a compelling compromise because we can ultimately decide on the number of radio frequency chains that we want to use on the basis of the number of antennas activated. So multi-set space-time shift keying fits into this family, and the idea is that we have essentially two different tunnels, if you like, in the transmission chain. We've got the space-time shift keying scheme, and we've got an antenna selection unit, and of course we can combine this with potentially arbitrary modulation schemes as well. So this becomes a very flexible scheme, as is seen in this simple nomenclature. We've got M transmit antennas and N receive antennas, and we spread the information over T time slots, and NT is the number of transmit antennas activated as seen here in the schematic. And just to mention that MC is the constellation size, and the number of antenna combinations that we can actually generate is denoted by NC. So we have a huge variety of potential schemes that we can design. The trouble is, however, that the complexity, I mean the detection complexity, becomes relatively high. And so in this treatise we also proposed a reduced complexity solution that can work as well as the optimal maximum likelihood detector. So let me elaborate a little further, although this is a busy schematic. In the top left-hand corner we can see the original space-time shift keying scheme, and so after this serial parallel converter we've got the classic MC array modulation scheme, and the second tunnel is constituted by a scheme where we select 1 out of AMQ number of dispersion matrices. Of course, the design of the dispersion matrices has also a substantial impact on the achievable performance. And so now this scheme is embedded into our multi-set space-time shift keying encoder. And again, just to mention that depending on the specific design of the scheme, it is possible that we get correlation across the symbols, and therefore we try to minimize this correlation, as I will highlight in a minute. So let's for a moment talk about how many bits we can convey with the aid of the different antenna combinations. So the size of the information symbol transmitted by the STSK scheme is determined by the parameters MC and NC, and so ultimately it's given by log base 2 MC times MQ. By contrast, the size of the information symbol transmitted by the antenna combination index is determined by the total number of antenna combinations given by this simple formula here. And so in this illustration we can see the bits per channel use, and as a function of the activated transmit antennas, in other words the number of radio frequency chains. So let's move on and deal with this correlation problem I alluded to briefly. Again, the reason is that if we use one or more common transmit antennas in the same space-time shift keying code word, this potentially imposes correlation, and that degrades to a degree the achievable performance. And so another feature of the proposed solution is that we introduce a phase rotation e to the power j phi c. So for a classic BSK constellation, the phase rotation is seen here at the top right hand corner, whereas for a QAM constellation at the bottom right hand corner. So just go back for a moment again. The rotation is seen here in the schematic, and there are other schemes that could be used to mitigate this problem, but this solution was found to perform quite well. So we're almost done, just really to look at the achievable performance and compare the classic STSK and the multiset space-time shift keying scheme. So the proposed scheme is represented by the continuous lines, whereas the benchmarker is by the dashed lines. So let's compare, for example, the clubs, which is the top configuration here, and the corresponding STSK scheme. There is about 5 dB, or in fact in excess of 5 dB gain at 10 to the power minus 5 for the system advocated. So just to look at finally the associated complexities as well. So at the top we have the achievable throughput, which is 4, 5, 6 or 7 bits per symbol, and down here we have the space-time shift keying and the multiset space-time shift keying, and just comparing, for example, a throughput of 7 bits per symbol. The space-time shift keying scheme requires 26 dBs, whereas the advocated scheme requires 21 dBs signal to noise ratio to achieve a bit error ratio of 10 to the power minus 5. And this comes to a degree at a slightly increased complexity order. For example, if we compare our favored solution, then the complexity order is 32 here, and it's 16 for STSK. As I mentioned at the beginning, there's a large variety of spatial modulation schemes, and this compelling scheme allows us to strike a compelling compromise between the achievable performance and the complexity imposed. So my hope is that you would enjoy reading the paper.